Well, again, folks, today I'm going to cover a section for the MAT-090 supplement. And basically, this will be a little bit shorter than the other video that you had seen, the other two, because it's just mostly a review. And you're not responsible for any other, homework. Just the homework that you have in my lab is sufficient. This is just an extra. Today is, looking at the calendar. Today is Friday the 29th. I know I didn't write that I was going to do an 090 today, except that it just seemed appropriate from the last material yesterday, 1.3 and 6.3. That is the beginnings of algebra, at least in our class. So I figured I would do that today. And I'll keep it somewhat unscheduled for that reason. Sometimes it won't be necessary. Let's see. Oh boy, I'll put that back here. Anyhow, I'm going to try to keep the board in this orientation. It's a little darker than I would like it, but I think not to have to turn it around when I use my projector, this would be better. All right, hopefully it's not too grainy. And I'll only know after the video is recorded, so we'll see how it goes. No juice here. Alright, I'm going to fire this up. You know what, maybe that's not necessary. Let me leave that be. The packet, you know where to look. The packet for today will consist of these pages, which is, I keep telling you, look in either pages in our Canvas course tile, or you could just go through announcements where I'll put the video link. I'll always link the materials. This is a very old diagram that I drew. It's an overview of basically the differences and some of the similarities between expressions and equations. A second page is sort of more or less a scaffolding. This is what I use when I'm mentally, when I'm trying to solve an equation. You don't have to do it anyway, this particular style of writing things, but it is a good resource. Then there are two word problems from the presentation that I had began yesterday. I want to go through these because they are something that would employ the techniques that I'm talking about today. Right, this question and this question. That's when I need my projector, really. Okay, so let me reiterate this because, as I said, this is very old. I made this about 13 years ago. I think I could improve it now. Well, so I hope. Anyhow, let's get started. All right, let me get rid of this. So we take some encroaches here. In the subject of algebra, there are two basic types of problems that you are inclined to see, or likely to see. The first are expressions. I had alluded to this yesterday. And the other type are equations. And let me just give a little line here, separate. That's not so good, that one. What does it consist of? Well, these are the building block. Think about it that way. The building block from which you make other things, specifically equations. All right, and so they consist of numbers, letters, potentially, if it's algebraic, and for sure, operations usually is a combination of a letter and a number. You could have, technically, something would qualify as being an expression, even if it's just a standing alone number. Similarly, if it's just a free-floating, seemingly free-floating letter, all right, that is considered an expression, all right? When you have the two of them in tandem, it's usually an operation that is in between them somehow. Whether it's adding, subtracting, multiplying, or dividing, or perhaps raising it to an exponent. The letter or the number. All right. Anyhow, do think of these again as the building blocks. All right. And for the sake of contrast, the equations are the house, you know, or the building, or what have you. All right. They are made from these parts. Anyway, I would encourage you to make this distinction yourself in your mind, because if you identify that you are dealing specifically with this type of thing, you will follow a specific set of rules. Whereas if you're solving an equation, you know that you're dealing with this, you will follow a different set of rules, which unfortunately bears some similarities. So it's confusing. People go, well, I don't know. They understand rules, they just don't know when to apply them. So let me give you some examples. And let me finish this thought, actually. What is an equation comprised of? Well, all of these things and then one thing extra. All of this in a bag of chips. All this and an equals 2. All right. You can tell immediately that you are dealing with an equation because you see an equal sign. If you do not see an equal sign, you are not dealing with an equation. And again, you want to make that distinction because they technically follow different sets of rules and you don't want to make a mistake. So bear that in mind. Right? Look to see if there is an equals or not. All right? It will separate out an expression from an equation, or distinguish one from the other. Here's perhaps a better way to visualize that. If you can think of an expression as sitting on the left side of an equation, and then a second expression sitting on the right side of an equation. Each of these are expressions unto themselves, but the whole kit and caboodle, this whole thing, is in fact an equation. Right? That's why I say these are the building blocks, and this is the whole house. Okay? Sorry for the sloppiness. It's an N, nice looking. All right. Now let me give you some actual examples, not just verbal examples. If in fact an expression is, as I say, either a number or a letter or some combination tied together with an operation, then here are some examples of those. The number 3 is technically an expression. It would be more accurately referred to as a numerical expression, or perhaps, if you're going to tie it to a subject, an expression from arithmetic. X, on the other hand, is an algebraic expression because it involves a letter. Right? If you had these two together, you might see something like x plus 3. Right? Or something even more complicated than that, like x squared plus 7x, right, plus 3. Right? An expression, an algebraic expression, an algebraic expression, an algebraic expression. Right? Usually when you see them together, a number and a letter, there is an obvious operation of some sort. Sometimes not so obvious. Now, if you saw something like this, 3 bunched together with an x, right? The operation technically in between them is multiplication. We just don't bother to write the x because we wouldn't want to confuse it with the variable. Oh, and a lot of times we just, for the sake of simplicity, will not even put the dot in there. Okay. An equation, visually, would look something like this. Um, 2x equals 10, maybe, for example. Or maybe x on top of 3 equals 9. Something like that. That is an x, I swear. X plus 5 equals 7. X minus 2 equals 14. You see an equals, automatically you would identify this as being an equation. Okay. Now, why belaboring the point so much for distinction? Again, they follow different sets of rules. And so even if they don't explicitly tell you to do, such and such thing, you can intuitively know what to do if you can identify what you're dealing with. You'll hear phrases like this thrown around when we're talking about expressions. Simplify, or evaluate. It's usually one of those two instructions when we're vaguely referring to an expression. Solve, on the other hand, is the word of choice when you're talking about equations. Now, because equations involve expressions, again, they are made from them, you may end up having to simplify first, but ultimately you have to follow a distinct set of rules in order to solve them. It's different, and you'll see why in a moment. If I turn this light on, if that would help at all with the reflection. Maybe slightly. I don't know if that's drastically better. I don't think that's really helping. I don't want to cast a shadow either. Here, make this dichotomy as well. There's a set of rules, even a subset, if you will, of rules when you're evaluating. I'm going to just abbreviate eval. Okay, and simp. Okay. Essentially, when the instruction is to evaluate an expression, and it usually would be evaluate an algebraic expression, that means to do two things. It means to plug in a given value substitute, in other words, right? And then usually follow the order of operations. And since the order of operations is as important as it is, I'm going to write that in a different color. I'll remind you later what the order of operations is. You got a sip of water, and you can drink that in yourself. Okay. It's these two things. They give you a number that represents, say, the letter X, and then you stuff that number in place of wherever you see X's in the problem, and then you follow the order of operations. if you are expected to simplify an algebraic expression, it is a little different. Let's see if green shows up here. This usually entails, basically the purpose of it is to make the expression less complicated. Basically shorter, as concise as possible. Now, how do you actually do that? Most of the time, you end up having to combine like terms. So if I'm going to subscribe a number here, you add or subtract what qualifies as like terms. And then in some instances, and you sometimes do this before, use the distributive property. I'm going to give you some examples of each of those in a bit. That's kind of rule 0, right? I'm putting a 1 here just because you usually just have to go right to this, but there are occasions when you need to do this as a preliminary step. Okay. Okay. Now, when it comes to equations, you would be asked to, again, they use this phrase instead, solve. Often, as a teacher, a student will come up to you and never berate them for this, of course. They would say, when you say solve, do you want me to simplify? And as a technicality, you would have to go, well, no, it's an equation. You solve equations and you simplify expressions unless the equation has an expression that requires simplification first. But that is too verbose, you know. In ordinary language, we kind of use these phrases synonymously, simplify and solve, probably because they both begin with the letter S. But just go, yeah, but, all right, and then explain that, use this word for equations and use this word for expressions. And understand that solve is a different set of rules, really. When they ask you, do you want me to simplify, they're really asking you, without saying it, do you want me to get the answer? And when you give somebody a test or homework or whatever, you want them to get the answer, so technically they are correct. You have to learn to interpret what people mean, students, especially kids, right? The preliminary step here is to simplify if necessary, but mostly what you do is this. You are, in this instance, simplifying is making an expression less complicated, that is to say, it's shorter. To solve is to isolate the variable. Right? To identify the value. If you want to think of it as a model, it's basically you want this. You want letter equals number, essentially. One letter equals sign and then one number. That doesn't always happen, but that's the ideal situation. Anyhow, in technical jargon, you want to isolate the variable. All right. Now, the actual instruction, it usually entails doing this. Opposite operations. Which means that if you see adding, you do subtraction. If you see multiplication, you do division. This is a reason why when a kid is introduced to algebra for the first time, they usually, they go, well, you just told me that, I just got done use of people telling me that I have to add when I see the sign. All right, now you want me to do the exact polar opposite of that, and you go, yeah. All right, there's a reason for that, though. You do this to balance. the beauty of algebra, the gift of it, right, is that once you get comfortable doing it, you realize that, wow, I can get away with murder, practically. As long as you are consistent, whatever you do to one side of the equal sign, make sure that you do to the opposite side, and everything is fair and square, you know? Okay? As a preliminary step again, what you may have to do is simplify first. Each side independently. So I'm kind of squeaking that in there. Simplify each side of the equals independently if it is necessary. That is not always necessary. Just like it isn't always necessary to use the distributive property. All right? Anyhow, so what's really different here? What is the two different sets of rules that you're following? I'm sorry, I'm getting tongue-tied. What are the two sets of rules that you're following? Opposite operations are essentially what you use to solve, all right? The order of operations is what you use when you're trying to evaluate, all right? All right. Or in theory, when you're trying to simplify, the distributive property is really multiplication, you know? Anyhow, let me give you some examples now. And we'll get into explanation of what are like terms and so forth. Okay. Coffee. My face is like asleep. Order of operations. I'll put here. Odor. Yeah, that's not a word. The odor of operations. PU. All right. Order of operations. You probably have heard PEMDAS, capitalize please, which is an acronym. But then there's this also, which is essentially the same instruction, just a different technique for memorizing. Please excuse my dear Aunt Sally. Okay. These are different techniques for memorizing the order of operations. PEMDAS is an acronym. I think I shouldn't use red, does it conflict here? This is an acronym, a word that is made from the initials of the operations involved. Parentheses is exponents, multiplication, division, addition, subtraction. Whereas this is a different mnemonic device. Please excuse my dear Aunt Sally. All right, now I have nothing against PEMDAS except that it often makes people believe that, well, M is before D in the acronym, therefore I should always use multiplication or do multiplication before division, and similarly I should always do addition before subtraction, but that is not true. Right? In general, you want to do things that are isolated, grouped in parentheses as first. Right? Exponents, things that are raised to a 2 or a 3, or technically if they were in a square root, you would do those second, so kind of an amped up form of multiplication. And these two each, you would want to do third, right? But they are equally important. So when you're trying to decide which should you do first, whichever is far left. We read left to right, and our math is left to right as well, okay? So you do whichever is on the left, and if you don't, then even if you add correctly, or if you subtract correctly, or if you multiply correctly, or if you divide correctly, you will get a different answer than somebody else. It's sort of like somebody may know how to drive, but they decide to go through red lights and stop at green lights. It's not what we all agreed to, right? So you do whichever is on the left in the problem, not left here or left there, right? The unique problem. Similarly, addition and subtraction are equally important. So you do whichever is on the left first, right? That does not mean and as in that's on the left side here. It means in the problem. In the problem. Okay. Now for the sake of contrast, as I mentioned before, when you're solving equations, you use opposite operations. Opposite operations basically cause cancellation. How else should I say it? Which is basically, they cause a simplification. They create balance. Right, so if you see a problem, even if it starts out written as such, that you see a plus sign, all right? If you want to cause cancellation or something to simplify, 2 L's I think it is, what you end up doing is its opposite, which is subtraction. All right? If you see subtraction, then you end up often doing addition. All right? If you see multiplication, then you end up dividing. And if you see division, then you end up multiplying. It's like that for more complicated operations as well, like exponents. Anyhow, usually, to further distinguish these, it's usually these two that you end up doing first, right? And these usually second, right? Whereas, where do you do addition and subtraction when you're dealing with expressions and the order of operations? You usually do those dead last, right? To complete this thought, last, fourth, yeah? So, add to subtract first, add to subtract last, okay? Make that distinction. This is why people get their answers incorrect. Because there are conflicting sets of rules. Now the last thing before I give you an example, and I'm going to put it under this heading still, is what if you're dealing with something that is purely algebraic, which means there's just letters involved? Well, there'll be numbers perhaps, but mainly letters. That is to say, what do you do when you have to simplify like terms? In order to, basically, when you're simplifying like terms, what that usually means is that you're adding or subtracting. All right? But you can only add or subtract when they are the same letter, and if you examine the letters that are involved, the letter has the same degree, which is referring to the exponent. So for example, if you had x squared plus x squared, then you would simply write this as 2x squared, because it's 1 and 1, right? If you had x squared plus 3x, you would just get stuck with that. You couldn't write anything. You couldn't combine them because they're not technically like terms. Yes, they're both x's, but that is a 1 for the exponent. Finally, let's do some examples. Simplify (3x plus 11 plus 7x plus 2). You're going to take this long, complicated algebraic expression, and you're going to whittle it down to something less complicated. You're going to shorten it. What I do myself when I'm trying to give myself sort of visual cues is I circle the things that I'm going to merge. So you could do 11 and 2 right off the bat, but just to complete this thought, like terms, this is a 3x and this is a 7x. These are like terms, which means you can add or subtract them because they are the same letter, and if you were to analyze their degrees, they would in fact be the same degree. You probably don't have to worry about that so much in this course, but it is something to bear in mind. So this is degree 1 and that's degree 1. Often math people don't bother to write them if they're not something greater. You just combined the coefficients. Coefficient is a fancy way of saying number sitting in front of a letter. Combine the coefficients. I think that's not really spelled so nicely, so I'm going to do this again. Coefficients. There you go. Still out of the frame. Close enough. Okay. So these two things have to be paired together. What is just 3 plus 7? 10, right? So it's 10x. Simultaneously, and just to distinguish it, I'll use a box. These regular ordinary numbers, which are referred to as constants, if coefficient is a fancy way of saying number sitting in front of letter, then a fancy way of saying regular number is constants. They don't have a number. Pardon me, they don't have a letter. So what is 11 plus 2? That would be 13, right? And this is your answer. Now, you might notice that I encapsulated the symbol that is the plus signs into when I put a box around this and a box around that, when I put a circle around this. It's sort of a reminder to me that the sign really should be associated with the number that is adjacent here on the right side of it. Okay? If you were dealing with integers, negatives and positives, it would be more of an issue. You really probably wouldn't even worry about it in a case like this, but it's a good habit to always group the plus or minus with the digit to the right of it. Okay. Let's see. Let me get a drink. Okay. That's enough of that. My shirt collar is a little too tight. Just do this. Alright, let me turn my projector on now because I want to show you that handout that I had made. And I'll turn this light off. Here's the homepage of the school campus. Where do I have it here? Okay, this document is what I'm after. Okay, it is a scaffolding. You don't have to do, when you're solving equations, you don't have to do it this way per se, but I think it is useful. So I'm going to show you how to do 4 one-step algebraic equations, and then I'm going to show you 2 slightly more complicated ones, and I'll do it on this piece of paper. All right. It's basically the second part here. I'm projecting basically this image. So, let me go back and discuss those single-step algebraic equations from before. I just kind of used them as an example, but I didn't do anything with them. I'm going to put them, you see how there's a dashed line here? I'm going to put x plus 5 above this dashed line on the left side of the equals, and then I'm going to put a 7 here. All right, and for the alternate example here, x minus 2 is equal to 14. When I get to the other two, it's a little bit more cumbersome the way that I wrote it, but I'll put 2x plus equals 10 here, and x over 3 equals 9 down here. Okay, now, since we're dealing with solving, we're going to perform opposite operations. All right. Firstly, and then second to both sides, right, for the sake of balance. Right? If I want to justify moving something over equals, right, if you're going over, then you really must employ an opposite operation. If you were, for whatever reason, sticking around on one side or the other, then you do simplifying technically, and you're just going to use regular operations. Anyway, what is the opposite of adding 5? The opposite of adding 5 is to subtract 5. So if you did it here, you are obligated to do it here for the sake of balancing. You can get away with murder and math as long as whatever you do to the left side, do to the right side. Right? And the effect is, there's a cancellation effect. What's 5 minus itself? Zeroes out, right? So if it zeroes out, you don't have to put a 0 here. It's no sin if you do that, but it is superfluous. If we're trying to really get the answer as concisely written as possible, just write what is left over here. X is left over on this side, so I'm bringing it a little bit closer, and I'm going to do the subtraction. What is 7 minus 5? 2. Okay. That is a one-step algebraic equation solved using subtraction. Now this starts out as a subtraction problem, at least it looks like it. But again, if you're trying to move this from here to here, if you're going over equals, you have to employ an opposite operation. In order to do that, you would perform the opposite of subtraction, which is, in this case, to add. So if I add here, for the sake of balancing, I have to add here. All right? What happens when you attempt to combine these two polar opposite magnitudes? That is, what happens when you add a positive to a negative of the same number? They cancel, right? Just like they cancel here, right? Do you have to write 0? No. What you should do is write what is left over as concisely as possible. So I'm going to scoot the x over here. What is 14 plus 2? 16. Okay. These two down here, this line here is no longer necessary, really. So I'm just going to scribble that out. Same thing here. This line here is no longer necessary. You're still going to, if you want to take this 2 to isolate the x, you're going over the equals. Someday over the equals. Yeah. Dorothy. Yeah. Anyhow, can you identify what is the operation of two things pressed together like so, a 2 and an x? They're technically being multiplied. So if you want to justify moving it over equals, you have to perform the opposite of multiplication. The opposite of multiplication is division. In algebra, they don't use the colon with the line so much to imply dividing. They just use this bar. Right? So you put a 2 here, and then you do it to the opposite side as well. There's a cancellation effect here, but it would maybe be more appropriate to call it simplification effect, because it isn't becoming 0, it's going to become what instead if you divide a number by itself. For the most part, it's just 1. You don't have to write 1 for the same reason you don't have to write 0. It's unnecessary, it's superfluous. So you could just simply write what's left over. What is left over? X. What is the outcome of 10 divided by 2? 5. And that is your answer. Over here you have a disguised form of division by 3. Right. And again, if you want to isolate the letter x, that is, get the letter x by itself to solve for the value, you have to move essentially this 3 over the equal sign. Now, how would you do that? Opposite operations. What is the opposite of dividing it is multiplying. And in a similar sense, that we don't use the colon with the line to imply dividing. When it comes to multiplication, they tend not to use x's, the traditional multiplication x, not to confuse it with a variable. So what you would see is a dot most often, and then the number, right? This is technically above the line, just like this is below the line, and there is that cancellation effect this way, right? If you multiply by 3 here, then you must multiply by 3 here. Your hands are tied, you're obligated, right? And the outcome, the leftover x, is the outcome of 9 times 3, which is 27. Okay? These are what are referred to as single step or one step equations. They're the basic 4. If you know how to do these, you're already ahead of the game. Let's do one that is a little bit more complicated than these two. Something that involves 2 steps, or maybe more than that. Suppose you had 2x plus 3 on the left and a 13 on the opposite side. Right. Now usually what happens is that you end up just having to do the adding or subtracting part first, because it's an equation. I should say this. You probably won't have to worry about it at this stage, right, in this course, or even in probably MAT 114. But as a preliminary step, try to simplify each side independently first. Independently is D-E-P and depend too many N's and E's and so forth in that. Try to simplify each side independently, then do the addition or subtraction, then do the multiplication or division. In this case, you really can't crunch this. They're not like terms. You're just stuck with it, and you pretty much will, that will be the norm. Come on. Okay. So I'm going to do what I had done before, but I'm going to do it in 2 steps. All right. I'm going to drag this 3 over to here. All right. I do so by opposite operations, which is in the case of opposite of adding 3, I'm going to subtract 3. 3's cancel. All right. What is left over? 2x is left over here. I'm not going to bother writing 0. It's superfluous. What is 13 minus 3? 10. I still don't have the letter x isolated, so it's not solved. So what I have to do is now the multiplication and potentially division portion here. What is the opposite of multiplying by 2? Dividing by 2. Dividing by 2. Whatever I did on the left, I have to do on the right. This is the balancing act that is algebra. This cancels down to 1. It simplifies, whatever you prefer to say. And the outcome is this coincidentally. X is equal to 5. If you had something like this, 8x minus 4, and then on the opposite side you have 7x plus 1, there's maybe an added step in here, right? Notice the distinction between this and the other problems. All the other problems discussed to this point had the letter X already on the left. In this problem, you see that you have X's on both sides. You need to choose one or the other. You could bring the 8 over here if you like. That is the whole thing, 8x. And just have X's on the right side. My intuition is always to bring it to the left. It doesn't have to be that way. Let's do the easy part first. Let's move this -4 over to here. What is the opposite of subtracting 4? Adding 4, and I'm going to strategically park it underneath the thing that it most closely resembles, which is the other constant. These are like terms. Cancels here. And I'm going to rewrite what is left over. There's an 8x. There's a 7x. And then these two would just end up being what? 5 plus 5. Now that I have decided, whether intentionally or not, that numbers without letters are going to be on the right, I have no choice at this point. Now I have to bring this over here, because I'm past the point of no return. So I'm just going to build another little table here and do that. And I'm going to attempt to move not just the number, but the whole term. That is the whole kit and caboodle, the 7 and the x, simultaneously over to here where its buddy is. Right, like terms. In order to accomplish that, it's not going to be any more complicated than adding or subtracting. I know it has a letter attached to it, and you may think that, oh, that's just multiplying and dividing. No, if you're taking the whole thing, the whole term, it's just adding and subtracting nonetheless. Just decide, what is the sign here if it's not written? What do you assume it is? You should assume, if there is no sign written here, that this starts out as a positive. So therefore, if you want to justify moving the whole thing from here to here, you're going to subtract it. There's going to be a cancellation effect once again. What is something minus itself? Even if it's mysterious. Yes, I don't know what x is yet, but it doesn't matter. By sheer logic alone, what is something minus itself? It cancels, and then you have 8 minus 7, which is really just 1 with an x attached to it. For the sake of simplicity, I'm just going to write the letter x, right? And therefore, what is the answer? It's just coincidentally x equals 5. Right? Two different problems that ended up coincidentally being the same thing. Okay? So there's a lot of nuance here. All right. Let me do those 2 word problems and then I'll stop. Okay. Okay, now hopefully that isn't too blurry. What I'm projecting here is the it's this slide that I had decided to skip yesterday, because we did a similar type. All right, now this is an example of you translating a word problem into an algebraic equation. And in order to do that, we're going to interpret everything in terms of one letter, right? Let me follow some of the technique I had suggested yesterday, all right? Let's draw our attention, literally draw our attention to the key features here. This says the sum. So if you have a sum, all right, that means that 2 things are going to be added, all right, minimally 2. The sum of what? Of 2 consecutive odd integers. Right? Consecutive means one immediately follows another. All right? If they are odd numbers are, let's see, 1, 3, 7, 9, 11, 13, and it goes into infinity. And then there's the symbol, the word is here, which is equals, right? As I was telling you yesterday, if you zero in on the word equals, this qualifies immediately as an equation, and anything that came grammatically before that is the left side, and anything that follows it is the right side. Right. So let me just try to translate what's written here. Right. Two consecutive odd integers. If we're going to just vaguely refer to something as an integer, let me call it I. Right. If there's two of them, this is where we have to explain everything in terms of one variable. It isn't wrong to go, well, it's a sum, so therefore it is a first thing plus a second thing. You could start out that way, all right, and then whittle it. But let's call the first thing I. And then, because we're talking about things that are odd, how far apart are they consistently into infinity? To get from 1 to 3, you would add what? 2. I skipped 5. To get from 3 to 5, you would add 2. To get from 5 to 7, you would add 2. To get from 7 to 9, you would add 2, and so forth. So when we're trying to explain the second thing in terms of the letter I, we would go, well, it is going to be I plus an additional 2. We're vaguely referring to it because we don't know what it is, but this is as concise and a way that we can talk about it. Right? So, first thing plus second thing. Then on the opposite side, we have, and because it's getting messy, I'm going to clean up a little bit. On the opposite side we have of equals, we have this phrase. We have 19, we're going to have to incorporate the phrase more than, which is counterintuitive. Whenever you see more than or less than, just realize it's counterintuitive. It means that even though this shows up first, you're going to have to stick this behind something. It's more than 5 times the greater of the two integers. Okay, so that's a mouthful. The greater of the two integers was originally, the second integer has to be bigger, right? Because it's going to be plus 2. I'll write it down here in a moment, but I'm going to stick with the vaguer phrase for a moment. It's 19 more than that. It's 19 more than 5 times the second. So the operation for more than is indeed plus, but don't technically put 19 plus that. You have to put it behind it because the phrase more than is comparative, and yes, English is confusing, but even though it shows up in front, it must go behind it because of the way it's phrased. All right. So, sticking with the symbols that we have here, the second is not written as second, it's written in algebra. So it's I plus 2. And instead of using 5x, I'm just going to put a 5 out in front. And then a 19 after it. This is the algebraic equation that we will use to find the value of both of these variables, of both of these consecutive odd integers. Because it's messy, I'm going to clean up a little bit again. All right, now remember the advice I had suggested before. Try to combine what you can. Simplify each side independently of the other. These parentheses I used really just to make it obvious that they're distinct things, but they are superfluous, so I'm going to move them now. This is one I, and this is one I. So how many I's do you have? You technically now have two I on the left side, because these are like terms. We're just combining them. They're an expression as long as we're sticking with one side or the other independently. Then there's a plus 2 adjacent. Over here, if we follow the order of operations, our attention would be drawn to the parentheses. These are not like terms, we're stuck with them, I plus 2. But there is a 5 out in front, which is, if it's pressed together, it means multiply. We would technically employ the distributive property here and here before we do anything else. So if it's 5 times I, it means 5I. If it's 5 times 2, it means plus 10. And then there's this free-floating 19 here. And now we will simplify these two things. I think I might put the light back on for a moment. There we go. And continue. These are like terms, they're both constants. So I'm always going to simplify like terms before I start playing the game of algebra. I'm going to play the game of arithmetic. This is really 2I plus 2 is equal to 5I, 19 plus 10 is 29. And now you see that you have one of the more complicated algebraic equations. So I'm going to build a table, and I'm going to go through the process. I'm going to put the 5I over here and the 2 over here, just because I like, it's a personal preference, letter equals number as the arrangement. Let me do the 2's first. If I want to drag the 2 from where it is over to where its buddy is, I'm going to perform the opposite operation of adding 2, which is to subtract 2. And then I'm going to strategically park it underneath the thing that it most closely resembles, which is another regular ordinary number, a regular constant. These cancel. Right? 2I is left over. 5I is left over. 29 minus 2 is, what is it? 27. So I'll be plus 27 here. Okay. Now, having made the decision, the executive decision, that I like numbers purely on the right, I have no choice. I really have to bring the i's over here. So I'm going to continue. Again, in order to justify moving this from here to there, I'm going to acknowledge that this is a positive if it's not written. So therefore, to justify moving the whole chunk, I'm going to subtract 5i. And then plop it under here where there's a second 5i. These 5i's are going to cancel. I'm going to be left with a 27. And then over here, this is technically a more complicated problem than you would see because it involves integers. If there's no sign, again, this would be positive 2. You can verify this with a calculator for now if you want to. But these are like terms. They're both the same letter I, and they're both technically I to the first degree. If you see one of each, that means you actually subtract. So you're going to get a 3 from the subtraction. You take the sign of the larger magnitude, that is the 5 in this case, so it's a negative 3i. Now, again, I'm going to erase a little bit for the sake of space. What are we left with? We're left with this. we're left with minus 3I is equal to 27. And again, it is understood that if you have two things pressed together like this, that they're being multiplied. So therefore, if I want to solve finally for I, in order to bring this 3 over here, I'm going to divide instead by negative 3. 3's cancel, a negative divided by a negative cancels, that's integers. And now I have this. This is technically a positive 27 and a negative 3. You can use your calculator again because we really didn't go into the discussion of integers here. But the set of rules for integers for adding and subtracting is also different from the set of rules for multiplying and dividing. When you have one of each, that just means that the answer is going to be negative. All right? 27 divided by 3 is 9. So that means that I is equal to negative 9. If the second integer is I plus 2, what would have to be the thing that follows it? What's negative 9 plus 2? Negative 7. Those are your two integers. Okay? Alright, we'll do one more, and I'll stop. This is the second sheet in the packet that I have for you today. A little bit more blown up here. And this is something that we may need to apply a little logic here, right? I'll turn the light off for a moment. The section of PVC pipe is 12 feet. So immediately you see this means that a pipe equals 12 feet to make it more concise. And if you don't like the unit for right now, you don't even need to worry about it. A plumber cuts it into two pieces. It doesn't say equal, doesn't say half, all right? It just says two pieces, which means it may be one long one and one short one, you know? Such that one is 2 feet shorter than the other. Already we see that there's inequality here. So we have a total length that is equal to 12. And the total length comes from, logically, without them explicitly saying it, two things that are really being added together would equal this total. Right? The first thing, the second thing. This is another instance where you have to explain everything in terms of just one letter, not two letters. You can start out with two letters. You can call this X and you can call this Y. All right, if you like. Say, all right, this is the first thing, and this is the second thing. Second length. But ultimately, you have to explain it in terms of just one letter or the other. All right, so how do we do that? We're going to use this phrase. 1, which I'll call X, right, is 2 feet shorter. This is a comparative phrase again. It's 2 feet shorter than, I'll stick with my own coloring system here. X, it's 2 feet shorter than the other, which is Y in this case. I just arbitrarily chose X's and Y's just to make them distinct for the moment. If this is a comparative phrase, this is again an instance where it would be counterintuitive. Alright, which means that even though, this shows up in your face first, that 2 is going behind something. Shorter than means subtraction. It's a vague way of implying that. So, X is this. Down here, I'm going to squeak this in. X is Y, the other, quote unquote, minus 2. And now I have an equation. how long is each piece? We can figure out both of them, but I'm gonna clean up a bit first. And now turn the light back on. We have established that the first thing is called x, and that x really represents y minus 2. And the second thing is just simply called y, right? And that they combined add up to 12. So I have this equation. I have essentially y minus 2 plus y equals 12. I'm going to turn the projector off at this point because it isn't necessary anymore. Okay. It's going to be light. Okay. And again, I have a situation where I have some like terms that I should attempt to combine before I start dragging things over equals. That is, I will perform arithmetic before I perform algebra. It is foundational. So this is a like term, and this is a like term. They're the same letter. They technically are y with a 1 in front. We just don't bother to write that. What is 1 plus 1? It's 2y. Minus 2 is left over, and this equals 12. And now I have this two-step algebraic equation. So I'm going to build a little table to get through this. I am going to isolate the letter y by moving the 2 first, by adding. There's the cancellation effect. 2y would be left over. Is equal to 12 plus 2 is 14. And lastly, I'm going to get rid of this 2. I'm going to drag it over to here by doing the opposite of multiplying, which is to divide by 2 and divide by 2. And therefore my y value is equal to what the outcome of 14 divided by 2 is, which is 7 feet apparently. All right. So this is really 7 feet. If x is 7 minus 2, what is x then? X is really 5 feet. Those are your two answers. And that makes sense, right? Because what's 7 plus 5? 12. Okay? All right. That's it for now. All right. This is again a review for 090. There is no additional homework than just what you see in my lab. But really what you need to do is just make sure, since this is the first week of school of the semester, try to establish a MyLab account if you hadn't, and work on those assignments that we have discussed to this point. So what does that mean? It means that ideally you will be working on these assignments, 1-1, 1-2, 1-3, and then 6-3 happens to be in 2 parts. So the due date is the day of the test, basically, in second week of February, I believe it is. But you have a little bit of time, naturally, but don't let it get out of hand. There is always a person in my classes that on midnight, they go, hey, I didn't know, and then they have to do 12 assignments. I'm like, how did you think that this was a good idea? All right, don't do that. All right, so anyhow, have a good weekend, all right, and I'll talk to you again on Tuesday, most likely. Be careful out there.